Today, August 5th, 2026, NASA just published something about Voyager 2 that almost nobody is talking about yet. If you care about what is happening at the very edge of human reach, in space, subscribe right now, because what just happened with this spacecraft changes what we know about interstellar space. Let me give you the full picture. Voyager 2 is over 13 billion miles from Earth right now. Think about that number for a moment. 13 billion miles. At the speed of light, a radio signal from NASA's Deep Space Network takes over 19 hours just to reach it. Then, another 19 hours to receive any reply. So, when engineers send a command to this spacecraft, they wait nearly 2 full days to find out if it worked. Before we reveal exactly what happened, take a second to subscribe to the channel and help us reach our goal of 1,000 subscribers. Your support allows us to keep bringing you the latest space discoveries and the incredible stories happening far beyond our solar system. And on August 4th, 2026, they found out that it worked. NASA's Jet Propulsion Laboratory just confirmed the success of what the engineering team nicknamed the Big Bang, a risky, simultaneous, all-or-nothing power management overhaul performed on Voyager 2. It was months in planning and had zero room for error, because if it had failed, Voyager 2 would have lost another science instrument before the end of this year. Instead, the Big Bang succeeded. Voyager 2 now has enough power to keep 3 science instruments running in interstellar space for at least another year beyond what was previously possible. And those 3 instruments are sitting over 13 billion miles away, in an environment that no human-made object had ever entered before. Voyager 1 crossed the boundary in 2012, measuring things about interstellar space that cannot be measured any other way, from anywhere else. That is what happened today. And to understand why it matters as much as it does, you have to understand what Voyager 2 actually is, where it actually is, and what it has been finding in the space between the stars that nobody knew existed before it got there. Voyager 2 was launched on August 20th, 1977, 17 days before its twin, Voyager 1, which launched on September 5th of the same year. The reason Voyager 2 launched first, even though it carries the number 2, is that it was sent on a slower, longer trajectory designed to take advantage of a rare planetary alignment that allowed it to fly past Jupiter, Saturn, Uranus, and Neptune in a single mission. That alignment only happens once every 176 years. NASA called the path the Grand Tour. Voyager 1 was sent on a faster route that only included Jupiter and Saturn, but would allow it to reach interstellar space sooner. Both probes were originally designed for a 5-year mission, yet neither of them has stopped working. Voyager 2 is now nearly 49 years into a mission that was supposed to last just 5 years. It visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It remains, to this day, the only spacecraft in history to have flown past the ice giants Uranus and Neptune. Everything we know about those planets from direct, in-person observation comes from a spacecraft that was built in the early 1970s, launched before personal computers existed, and is still operating today on a fraction of the power it started with. Power is the core issue that has been defining the Voyager mission for the last several years. Both probes use radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. They are essentially nuclear batteries. Back when Voyager 2 launched in 1977, those generators were producing around 470 watts. Every year since, As the plutonium has continued to decay, output has dropped by about 4 watts per year. After nearly half a century, the power available to Voyager 2 is now so limited that every single watt has to be accounted for. The engineering team has been working through a carefully prioritized shutdown sequence for years, turning off heaters first, then backup systems, then science instruments one at a time, each in an order agreed upon by the science and engineering teams, based on which instruments were still returning useful data from interstellar space, and which had effectively completed their mission. Scientific purpose after the planetary flybys ended in 1989. Voyager 2 originally carried 10 science instruments. By the beginning of 2026, through a series of planned deactivations over many years, it was down to just 3 active instruments: the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem. Without the Big Bang intervention that JPL has now confirmed as successful, the cosmic ray subsystem was scheduled to be shut off before the end of 2026, reducing Voyager 2 to only 2 operating instruments. Instead, the Big Bang has bought at least another year for all 3. What exactly is the Big Bang? JPL engineers describe it as a simultaneous swap of powered devices. The spacecraft had been using 3 heater units to keep its thruster fuel lines from freezing, because if those lines freeze, the thrusters stop working. Without functioning thrusters, the spacecraft can no longer point its antenna toward Earth, and the mission would effectively end forever. During the Big Bang procedure, engineers switched those 3 heaters off, while simultaneously activating 3 alternative devices that provide the same thermal management, but consume nearly 10 watts less power in total. 10 watts may not sound like much, but for a spacecraft operating on razor-thin power margins and losing about 4 watts of electrical output every year, it is a massive gain. That single improvement is enough to delay the shutdown of another science instrument by at least 1 year. The reason this operation was so risky is the extraordinary level of precision it required. The changeover had to happen simultaneously, not one step at a time. If the alternative thermal management devices failed to activate quickly enough after the heaters were switched off, the fuel lines could begin cooling toward dangerous temperatures before protection was restored. To reduce the risk, engineers first tested the entire procedure on Voyager 2 during May and June of 2026. Voyager 2 was chosen because it is closer to Earth than Voyager 1, making the command and response cycle slightly shorter, and because it still had a small amount of additional power available, making it the safer spacecraft on which to attempt the test. The tests were successful, the full implementation worked exactly as planned, and NASA officially confirmed the achievement on August 4, 2026. The agency now plans to perform the same Big Bang procedure on Voyager 1, which is currently more than 15 billion miles from Earth and takes over 23 hours to receive a single radio signal. Now, here is the part that explains why all of this matters scientifically. Voyager 2 is not simply drifting through empty space. It is carrying out measurements that no other spacecraft humanity has ever built can perform. It is directly sampling the local interstellar medium, the region of space that lies beyond the heliosphere. To understand why those measurements are so valuable, you first have to understand the heliosphere itself, one of the largest and most important structures in our solar system, even though it cannot be seen with the naked eye. The heliosphere is an enormous bubble of charged particles and magnetic fields created by the Sun. The solar wind, a continuous stream of charged particles flowing outward in every direction, inflates this giant bubble until its outward pressure is balanced by the pressure of the surrounding interstellar medium. The point where those two forces finally reach equilibrium forms the outer boundary of the heliosphere, known as the Heliopause. Inside the Heliopause is the Sun's territory. Everything inside it, the 8 planets, the asteroid belt, the Kuiper belt, and all the smaller bodies of the solar system, exists within the Sun's protective bubble. Outside the Heliopause lies true interstellar space. The heliosphere performs a critically important function for life on Earth by partially shielding the solar system from galactic cosmic rays. The extremely high-energy particles constantly streaming through the galaxy from exploding stars, colliding neutron stars, and other violent cosmic events across the Milky Way. Without the heliosphere acting as this protective barrier, the amount of cosmic ray radiation reaching the inner solar system would be significantly higher. In other words, the planets inside the heliosphere exist within a shield that the Sun itself continuously creates and maintains. Understanding how that shield works, how thick it is, how much it changes over time, and how it interacts with the interstellar medium pressing against it from outside, is essential to understanding how habitable our solar system remains over astronomical timescales. Voyager 1 crossed the Heliopause on August 25, 2012, at a distance of about 121 astronomical units, AU, from the Sun, with 1 astronomical unit being the average distance between Earth and the Sun, roughly 93 million miles. Voyager 2 crossed the Heliopause on November 5, 2018, at approximately 119 astronomical units, following a different path through the heliosphere and crossing the boundary from another direction. When Voyager 2 made this historic crossing, something remarkable happened. Voyager 1's plasma science instrument had stopped working back in 1980, meaning it could not directly measure the plasma environment during its own crossing. Voyager 2, however, still had a fully functioning plasma science instrument. For the first time in history, humanity was able to directly measure the plasma environment at the exact moment a spacecraft crossed the Heliopause, and then continue measuring conditions in interstellar space on the other side. The data that came back surprised scientists. As Voyager 2 entered interstellar space, it measured the surrounding plasma at temperatures between approximately 30,000 and 50,000 Kelvin, roughly 30,000 to 50,000 degrees. Scientists had not expected temperatures anywhere near that high in the local interstellar medium. Before the mission, this region of space was believed to be relatively cold, sparse, and quiet. Instead, Voyager 2 found plasma that was dramatically hotter than theoretical models had predicted. The heliosheath, the region just inside the heliopause, where the solar wind slows before reaching the boundary, also turned out to have a very different structure than expected. Likewise, the termination shock, where the solar wind first slows from supersonic to subsonic speeds before eventually reaching the heliopause, appeared in a different shape and location than existing models had forecast. Even the heliopause itself was revealed to be far more complex than scientists had imagined. Rather than being a sharp, clean boundary, it turned out to be a layered transition zone, where physical properties change gradually across several distinct regions. What Voyager 2 has been measuring ever since entering interstellar space, and what its 3 remaining instruments continue to measure today, in August 2026, is the actual composition, density, temperature, and magnetic field structure of the space between our solar system and the nearest stars. Its magnetometer measures the magnetic field of the interstellar medium, confirming that interstellar space is far from magnetically empty. Instead, it contains magnetic fields carried by plasma released from dying stars over billions of years of galactic history. The plasma wave subsystem detects oscillations within the interstellar plasma, allowing scientists to calculate the density of electrons surrounding the spacecraft. This is the same type of instrument that, aboard Voyager 1, has been detecting persistent narrow-band plasma wave emissions continuously since 2017, enabling researchers to map changes in the density of interstellar space as the spacecraft travels farther from the Sun. The Cosmic Ray Subsystem, the third instrument still operating on Voyager 2, thanks to the success of the Big Bang power-saving procedure, measures the galactic cosmic rays constantly arriving from deep space. These observations, taken from beyond the heliosphere, allow scientists to determine exactly how effectively the heliosphere shields the solar system from these energetic particles and how that protection changes throughout the Sun's approximately 11-year activity cycle. During periods of solar maximum, when the Sun is most active and produces a stronger solar wind, the heliosphere expands slightly and provides greater shielding. During solar minimum, when solar activity decreases, the heliosphere contracts, allowing somewhat more galactic cosmic radiation to penetrate toward the inner solar system. Voyager's instruments in interstellar space can directly measure how the cosmic ray flux outside the heliopause changes over time, giving scientists the first true outside-in view of how effectively the heliosphere shields the solar system as solar activity rises and falls. The data is also helping answer one of the biggest questions about the solar system's outer boundary. What shape is the heliosphere? For many years, the Standard Model suggested that the heliosphere resembled a giant comet, with a long tail stretching behind the Sun as it moves through the Milky Way. However, the Voyager missions have challenged that picture. Voyager 1 crossed the heliopause while traveling roughly north of the ecliptic plane, while Voyager 2 crossed it heading roughly south. Despite taking completely different paths, both spacecraft crossed the heliopause at nearly the same distance from the Sun, between about 119 and 122 astronomical units. That similarity suggests the heliosphere may be much more spherical than earlier models predicted. At the same time, the two spacecraft observed important differences. Voyager 1 detected dramatic fluctuations in the magnetic field as it crossed the heliopause, while Voyager 2 experienced a much smoother transition. This indicates that the heliopause is not identical in every direction. Instead, the boundary appears to have different structures depending on where it is observed, showing that the heliosphere is not perfectly symmetrical. With only two spacecraft ever to cross into interstellar space, scientists currently have just two direct measurement points. Every additional day that Voyager 2 continues operating and sending data adds another invaluable observation to humanity's only in situ record of what the space beyond our solar system is actually like. The signals Voyager 2 sends back to Earth are astonishingly weak. Its radio transmitter produces only about 23 watts of power, roughly the same as a household refrigerator light bulb. After traveling more than 13 billion miles through space, that signal spreads across an enormous region before finally reaching Earth. To detect it, NASA's Deep Space Network antennas in California, Spain, and Australia work together to capture the incredibly faint transmission. Even then, the spacecraft communicates at only about 160 bits per second, a data rate comparable to the slow dial-up internet connections of the 1990s. At that speed, transmitting a single modern digital photograph would take many hours. Every scientific measurement Voyager 2 collects from interstellar space reaches Earth through that tiny trickle of data. Engineers at NASA's Jet Propulsion Laboratory manage this precious communication with extraordinary care. Some members of the team have spent decades working on the Voyager mission, while others were not even born when the spacecraft launched in 1977. Together, they carefully decide which data should be transmitted first, when to schedule each transmission, and how to conserve enough power to keep the spacecraft functioning for as long as possible. Following the success of the Big Bang power management upgrade, the immediate goal is to keep Voyager 2's 3 remaining science instruments operating through at least 2027, and potentially much longer if the spacecraft's aging hardware continues to cooperate. Engineers have also announced plans to perform the same Big Bang procedure on Voyager 1 in the coming months. If both spacecraft remain healthy, the mission could continue into the 2030s with at least one science instrument still collecting data. Another historic milestone is approaching. On November 18, 2026, Voyager 1 is expected to become the first human-made object ever to reach a distance of exactly 1 light day from Earth. At that point, a radio signal sent from Earth will require 24 hours to reach the spacecraft, and another 24 hours for any reply to return. A full 2-day round-trip conversation with a machine built by human hands nearly half a century ago. Voyager 2 is not expected to reach that same symbolic distance until November 2035. Current engineering estimates suggest it may no longer be operating by then, although the spacecraft has repeatedly exceeded expectations throughout its mission. What is truly at stake in keeping Voyager 2 alive is not simply collecting more data for its own sake. It is preserving humanity's only direct window into the very local interstellar medium. Every other measurement of interstellar space is indirect, obtained through telescopes analyzing starlight or missions such as the Interstellar Boundary Explorer, which studies energetic neutral atoms flowing back toward the solar system from the heliosphere's edge. Voyager 2 is different. It is physically inside interstellar space, surrounded by that environment, directly measuring its magnetic fields, plasma, particle density, and cosmic radiation from within. There is no substitute for those observations. No other spacecraft currently exists that can perform them. The next dedicated mission designed to explore interstellar space, if it is ever funded and launched, will not arrive there for decades. The next dedicated interstellar mission, if it is ever funded and launched, would take decades to reach the distances Voyager 2 has already achieved today. That means the data currently traveling back to Earth across a 19-hour one-way radio link is genuinely irreplaceable. Every watt of power saved by the Big Bang upgrade is far more than just electricity. It represents scientific measurements that cannot be collected by any other spacecraft or any other method, and may not be possible again for an entire generation. Think about what that really means. A spacecraft launched nearly 49 years ago, built with technology from the early 1970s, is still traveling through the space between the stars at roughly 34,000 miles per hour. It is still making discoveries, still transmitting data, and still teaching humanity new things about the universe that simply cannot be learned any other way. Few engineering achievements in history have demonstrated this level of durability, precision, and scientific value. Then, on August 4, 2026, a team of engineers at NASA's Jet Propulsion Laboratory sent a command that spent more than 19 hours crossing over 13 billion miles of empty space. After another 19 hours, the response finally arrived back on Earth. The message was exactly what they had hoped for.